Hello! Today we're going to study some organic chemistry. You may already affiliate that word organic with life on Earth, and in chemistry that means that life is carbon-based. We're going to study those carbon-based compounds. So today we're going to start with the naming, and we're going to look at how to name the main chain, and then we'll figure out some names of things to attach to the side of it. So for the main molecule, we have a prefix in the beginning that's going to tell you the number of carbon compounds, and then at the end we have the suffix that tells you whether it's a single, double, or triple bond. Looking at the prefixes, some probably look familiar from geometry, but pay attention to these first four: meth, eth, prop, and bute, special for our organic chemistry. The ending is going to tell you whether it's an alkane where there's only single bonds, completely only single bonds. An alkene would have a double bond and an alkyne would have a triple bond. So with naming, if it's an alkane, we use ane at the end, ene for an alkene, and yne for the triple bond. So the name is just the two parts. We have eth, meaning 1, 2 carbons, and ane, showing that single bond. If we changed it to a double bond, we would change the ending to ene. And if we changed it to a triple bond, we would change the ending to the yne. The other thing hydrocarbons can do, we can put those carbons in a circle. The main name stays the same. Since there's 5 carbons, I'll use the prefix pent, and the single bonds, I'll use the ane. And then when they're in a circle, we just use the prefix cyclo in front. So we would have a cyclopentane here. You might be starting to realize there's a lot of hydrogens. That's kind of the assumption that the attachments are hydrogen. You don't have to waste your time drawing millions of hydrogens. Just show the dashes to show where they are. But the one thing we do want to be careful about in the name is to show where things are. So say, for example, I had a double bond between the first and second carbon. I would name it 1-pentene. That 1 shows where that double bond is. If I moved the location of the double bond, then I just changed the number because now it's between carbons 2 and 3. So we use 2-pentene. The other thing, now that we've got some numbering down, we can look at when we have some branching going on. So not all the carbons are in a main chain. Maybe there's some splits. The base name still tells you exactly how many carbons, prop meaning 3, and what type of bond. A single bond for the ane. So I would draw 3 carbons in a row and make the bonds single. This number tells me where to attach my branch. The meth still represents the number of carbons, and then we just use this new little YL to indicate that it is a branch. So I would have a 1 carbon branch coming off. And then you would just add whatever hydrogens are needed for the octet. So here's our 2-methyl propane. When it comes to naming organic chemistry molecules, it can be a little tempting to treat it like reading and just read from left to right. But real molecules, they bend, they move, they flip. So one of the first rules with naming, you always find the longest chain. And it may not be the one that's straight from left to right. If you went left to right, you would only have 6. But if you go up this way, you can have 7. So we would name this as a heptene, and we would count 1, 2, 3. So a 3-methyl heptene. Another tricky thing with the numbering, again, we don't just want to assume it's from left to right. The rule here is that you want the lowest numbers possible. If I numbered left to right, I would number 4, 5, and 6 for these branches, but you can actually get lower numbers going backwards, where it would be 2, 3, and 4. You establish that one numbering system, whatever's the longest chain and the lowest numbers, that's the right name for the main chain. So in this case, the longest chain is the straight across 7 carbons, and the lowest numbers here are 2, 3, and 4. Then we just get to naming the branches. So wherever you have the 1 carbon branch, you're going to use that prefix meth. They're branches, right? So we use that YL. And then new thing, if there's 2 of them, we add a little prefix di. Or if there were 3 of the same thing, we could use tri, for example. This other branch has 2 carbons, so the prefix for that was eth, and then we use the YL for a branch. So we have ethyl and dimethyl so far. Now let's just put it all together. 4 was the placement for the ethyl. 2 and 3 are my placements for the dimethyls. And then the main chain with 7 carbons is named as a heptane. So this is a 4-ethyl 2,3-dimethyl heptane. Last rule, when you name things, always put it in alphabetical order, not with the di or tri, but the actual branch alphabetical order. So ethyl comes before methyl. It has nothing to do with the numbering. We just picked the lowest numbers. All right, last trick. What if there's a tie? If we went this way, 2 and 4, and then if we check backwards, it's also 2 and 4. So which one is it? Let's look at what our branches are called. 1 carbon methyl, 2 carbons ethyl. Alphabetical order is the tiebreaker. E comes before M, and so we would number backwards, making this 2 and 4. So a 2-ethyl and a 1-methyl pentene chain here. Okay, now there's a special group of carbons, hydrocarbons, that actually do smell good. That's why they're named aromatic. Actually kind of poisonous, so don't let it be deceiving. This little guy, benzene. So benzene, whenever you see this, you'll see this a lot in organic chemistry. It's the basis for a lot of different molecules. It's drawn like this with the 6-sided figure and the circle in the middle, but let's take a quick peek at what it really looks like. What it means is it's every other bond is double, single, double, single, double, single. But as you know, when there's double bonds that can move, you have resonance, and so that whole extra pair of electrons is delocalized. So since that actual moving around is happening, we just draw the benzene like this with that center ring to represent all those movable carbons, or electrons. So there's my resonance for benzene. All right, so now we've got the main chain, all the things that we'll use as our focus, and now let's talk about the attachments. We call these functional groups, different things that can attach to carbon. So first thing as we get into these groups, we're going to use the symbol R to represent any kind of hydrocarbon chain or whatever that main group is, and then we'll look at different attachments. The first of which are our halogens, which we typically use X for halogens. So it would be a hydrocarbon chain attached to like chlorine or fluorine, using prefixes fluoro, chloro, bromo, and iodo, respectively. So let's take a look at one. We'll start with the main chain, 1-hexene. So hex means 6 carbons. 1, 2, 3, 4, 5, and 6. The ENE tells me I have a double bond. So then I'm, double bond. So then I'm going to look over here to the 1 to see where to put that between the first and the second carbon. So I have double bond in the first place, single bonds everywhere else. Now I'm going to look at what my attachment is. Bromo tells me it's bromine. Di tells me there's 2 of them. And the 2 and 4 tell me where to put them. So I'll go to my second carbon and attach a bromine, and then my 4th carbon and attach a bromine. Everywhere else is just hydrogens to complete the octet. Be careful when adding hydrogens for a double bond. We wouldn't want extra electrons here. It already has 8 electrons, 4 bonds. And so for this carbon, it's just 2. So there's our 2,4-dibromo 1-hexene, just bromine attached. Next group, we have alcohols. Alcohols are based on hydroxides, so an OH group. With the hydrocarbon chain and you're drawing the dashes, you don't have to write the H, but if there's an H in a functional group, you do. So you're going to write in OH for these groups. So let's look at our first one. When we have an alcohol, we are going to change the ending to be OL instead. So starting with the main 1-bute, 4 carbons for bute. AN still tells me single bond, and now OL tells me I have a hydroxide. We use the number in front to tell me where to put it. So on that first carbon, there's my OH group. We can add other things too, like the 3-methyl, we would then count 1, 2, 3, and put on that 1 carbon branch. And then just use our dashes to fill up that octet. So here we have our 3-methyl 1-butanol. If the hydroxide group attaches specifically to that special benzene ring, then we name it a phenol. the word phenol takes care of the benzene ring and the hydroxide, and it makes that carbon the number one carbon. So then if we were to name another branch, we'd go from there. So now we'd be over at 2 to attach the methyl group. So this would be 2-methylphenol. Phenol being that main benzene ring with the hydroxide. All right, next, let's take our hydrocarbon chain and break it up with an oxygen right smack in the middle. So carbon groups on both sides of an oxygen. So when you do that, the name of the group then is an ether. So we actually have 2 ways of naming this, and I'll show you both. One is to name it as an ether, and one is to use oxy for where the oxygen is. So if I see methoxypropane, it's telling me 1 carbon, oxygen, and 3 carbons. So 1 carbon, oxygen, 1, 2, 3 carbons. Methylpropyl ether, another version of the naming. Ether tells me I have an oxygen in the middle of 2 carbon groups, and then these tell me basically what the branches are. One's a 3 carbon, one's a 1 carbon as branches, and you end up with the exact same structure. And either way you would do it, you would then surround your carbons with hydrogens. You're not assuming hydrogens on the functional groups. So either naming system works, whichever you prefer, and then we just have our oxygen in the middle for an ether. All right, next we have a family of groups that are all based on this double bonded oxygen. So if I have carbon double bonded to an oxygen off the side, and it's got just 1 carbon and the other is a hydrogen, then we call it an aldehyde. If we have the carbon that's got the double bonded oxygen attached in like the middle of the carbon chain, then we would call it a ketone. And then if it's part attached to carbon and the other half is hydroxide, then we call that whole thing a carboxylic acid. So let's take a look at one of each. So first up, I have our aldehyde, and kind of like we changed to OL for alcohol, we're going to change to AL for an aldehyde. Main chain here just still has 3 carbons, so we're going to use prop, and I see just single bonds. So we've got AN, and instead of ending with an E, now I'm going to end in AL. With aldehydes, you don't need numbering because that's the number 1 carbon, wherever that functional group is. So we don't need to not name it 1-propanol. That's like an insinuation already. With the ketones, though, you do need the number because it could be anywhere inside of the chain. The ending of the name is changed to this ANONE. So for example, if I have 4 carbons using bute, and then change this whole thing to a none, butanone. But it could be anywhere. Is it 1? Is it 2? Where is it? Well, I guess it couldn't be 1, but 2, 3, 4, anywhere inside the chain. So in this case, remember to check for backwards numbering. It would be on your 2nd carbon, so we would call it 2-butanone. And then last but not least, we have our carboxylic acids, where you have the carbon attached to both a hydroxide and a double bonded O. And so now the ending of the name gets changed to anoic acid. So if we had 1, 2, 3, 4, 5 carbons, I use pent and then change the ending to anoic acid. So pentanoic acid. By doing that, we automatically again make this the number 1 carbon. So if we had a branch, we would count back 1, 2, 3, and so this might be a 3-methyl pentanoic acid. So when the definition makes it the number 1 carbon, you don't add the number also. So just 3-methyl pentanoic acid. There is a trick to putting a carboxylic acid on benzene though. It looks a little different. It does have an extra carbon. In the other regular ones, you count that carbon as part of the chain. The reason benzene is different is it already has a double single bond. It can't also then attach another double and single bond and have like 6 bonds. So instead, we use the carbon to make that connection. Notice there's no acknowledgement. It's not like methyl anything. It's just assumed it has to be there because we know how the octet rule works, right? And then just like the others, makes that by definition number 1 carbon. So if you added a branch, you would count from there. 1, 2, 3. And that's benzoic acid. Our last groups are going to be based on the NH2 group, having nitrogen with 2 hydrogens attached to some other carbon chain. Except the first thing that we're going to look at actually is going to just have nitrogen in the middle, and we'll see what's attached to it with the rest of the name. So when you have nitrogen with other things around it, that's called an amine. And in this case, my attachments are going to be 3 1-carbon branches. So 1, 2, 3, carbon, carbon, carbon. And the carbons always come with their hydrogens. The functional groups do not, and you know there would actually be a lone pair there instead. All right, now let's look at that actual NH2 on a bigger chain. So in this case, bute tells me I have the 4 carbons, and then the ANE tells me I have the single bonds. Then I'm going to look at this new part where amino represents that NH2 group, and the 2 tells me where to put it. Come over to the second carbon and attach NH2. And the rest is hydrogen. So we have to write the H's for the functional groups, and you can leave the rest as dashes. And that's our 2-amino butane. Last thing we're going to look at is what if it's on that very, very special benzene molecule. So first, we draw our benzene, and then we attach the NH2. Whenever you see that, the base name is aniline, and this is, again, number 1 carbon, always. So then we would count from there to the 3rd and 4th positions. So either way we go, it's going to be 2, 3, 4, 5, or if we went this way, 2, 3, 4, 5, same position. And what we're attaching here, there's 2 chlorines. So I would have a chlorine here and a chlorine there, and this would be my finished little molecule for 3,5-dichloroaniline. And that's our last group. So that's Orgo in a nutshell. I really hope this video helped. Much better. Stop, 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 stop.